Hello, in this video we're going to go over a proof of Jensen's or Jensen's inequality and its applications. So the Jensen's inequality tells us that let I be an interval. If you have a function that is concave up, then for every x1 through xn in I and every w1 through wn in 0, 1, satisfying the sum of wi's is 1, we have f of sigma wixi is less than or equal to sigma wif of xi. We're going to use that and then we're going to apply that to a particular function to get to the AMGM inequality, weighted AMGM inequality, harmonic mean, geometric mean, arithmetic mean, square root mean inequality, and finally we get the power mean inequality, which is the strongest of these four inequalities that I have here. Okay, so first, what is a function that is concave up? So first I'm going to define what a function is that is concave up. I'll give you two examples of functions that are concave up. We'll prove Jensen's inequality and then we'll see the applications. Okay, so let's get started. So what is the definition of a concave up function? Before we can get to that, I would like to introduce the idea behind what a convex or concave up function is. So what is a function that is concave up? It basically means if you look at the graph of the function, it opens up. So how can we translate that into mathematical language? If I take 2 points x and y, let's just assume that x is less than y. If you take some point in between, let's call that z. We know that z would be a linear combination of x and y. In other words, you can write down z minus x as t times y minus x for some t between 0 and 1. So evaluating this, we get z is equal to ty plus 1 minus tx. Now, so this is the point z. So this length right here, this guy, is just f of that. And if you look at this portion from the bottom to this, we know that this guy is larger. If you write down the equation of this line and evaluate this length becomes t times f of y plus 1 minus t times f of x. So of course the green portion is greater than or equal to the blue portion, which is f of ty plus 1 minus tx. And this is the definition of a convex or concave up function. So let's write down the definition. So let I be an interval f from I to r is called convex or concave up. Is called convex if f of tx plus 1 minus ty is less than or equal to tf of x plus 1 minus tf of y for all t in the interval 0, 1 and for all x and y in the interval I. Notice that tx plus 1 minus ty is still in the same interval I because it's just something between x and y. So let's look at some examples. Here are a couple of examples of functions that are in fact convex. Absolute value of x is convex, and the reason is if you look at absolute value of tx plus 1 minus ty, this is less than or equal to, we can use the triangle inequality. This would be absolute value of tx plus absolute value of 1 minus ty, which is t absolute value of x plus 1 minus t absolute value of y. And this is because t is between 0 and 1, so which means t and 1 minus t are both non-negative. So that's the first example. Here's the second example, which is a really useful one. If f prime is increasing, then f is convex. And again, this function f, I'm assuming that f from I to r is differentiable over the interior of I. Okay, so why would that be convex? The reason is not very difficult to see. So let's look at the difference between f of tx plus 1 minus ty and tf of x plus 1 minus tf of y. So let's look at this difference. We can rewrite the first one as t times f of tx plus 1 minus ty plus 1 minus t times the same thing. So we can write it down as t times f of tx plus 1 minus ty minus f of x plus 1 minus t times f of tx plus 1 minus ty minus f of y. Now, I'm going to use mean value theorem. So this guy is equal to f prime of sum a, where a is between x and tx plus 1 minus tx, times tx plus 1 minus ty minus x plus 1 minus t times f prime of sum b times tx plus 1 minus ty minus y. And this is true for sum a between x and tx plus 1 minus ty, and b between tx plus 1 minus ty and y. And here we assume x is less than y. Okay, so this is by mean value theorem. Now I can simplify this, what I had up here, and write it down as t times f prime of a. So if you simplify that, we get 1 minus t. We can factor 1 minus t, and we get y minus x plus 1 minus t f prime of b. So from those two terms, we can factor a t, and we get x minus y. If we factor a t, a 1 minus t, and a y minus x, I would get f prime of a minus f prime of b. Now I know these three things are greater than or equal to 0. And I know that if I look at the points x, y, and this one is the tx plus 1 minus ty, a is here and b is here. What that means is that f prime of a minus f prime of b is in fact less than or equal to 0, because I assume that the derivative of f is increasing. So that means the difference that I had is going to be a negative number. So that means f of tx plus 1 minus ty minus tf of x minus 1 minus tf of y is less than or equal to 0, which means exactly what I want. F of tx plus 1 minus ty is less than or equal to t f of x plus 1 minus t f of y, which means f is convex. So if you have a function whose derivative is increasing, it would be convex or concave up. Now let's now that we understand convex functions and we have a couple of examples, let's look at the inequality, the Jensen's inequality. The Jensen's inequality. Okay, so we're going to prove the Jensen's inequality by induction. So let me first write down what it was. You have a function f from I to r that is convex. So this is the assumption. And also we have x1 through xn are in I, and then we have w1 through wn are in 0, 1, with sum of wj's equal to 1. Then f of sum of wj xj is less than or equal to the sum of wj f of xj. And this is again 1 to n. So we're going to prove this one by induction on n. For n equals 2, n equals 1, both sets are basically the same. It's really not interesting. So we start from n equals 2. Induction on n. So for n equals 2, we get f of w1 x1 plus w2 x2. This is equal to, now w1 plus w2 is 1. So I can write this one down as w1 x1 plus 1 minus w1 x2. And because f is convex, I can say this is less than or equal to w1 f of x1 plus 1 minus w1 f of x2, which is exactly w1 f of x1 plus w2 f of x2. So for n equals 2, it's basically just the assumption that f is convex. So now suppose the inequality holds for n. So suppose the inequality holds for n. Let's assume that we have n plus 1 numbers in I and n plus 1 weights. So assume x1 through xn plus 1 are in I and w1 through wn plus 1 are between 0 and 1, and they satisfy sum of wj is 1, j equals 1 to n plus 1. We're going to look at f of sum of wj xj, j equals 1 to n plus 1. And we're going to break this up into two different portions, and we're going to use inductive, the basis step, and then inductive hypothesis. So this is f of, I'm going to do 1 minus wn plus 1, and then the sum of wj xj, j equals 1 to n, and then divide that by 1 minus wn plus 1, and then plus wn plus 1 xn plus 1. By assumption, since these two add up to 1, this would be less than or equal to, this is the fact that the fact of n equals 2, or basically the assumption that f is convex. This is less than or equal to 1 minus wn plus 1 f of sum of wj over 1 minus wn plus 1 xj, j equals 1 to n, plus wn plus 1 f of xn plus 1. Notice that this quantity still belongs to I. And that's not very difficult to see, because if you look at this quantity, it's between the smallest xj and the largest xj. And the reason is sum of wj, j equals 1 to n, is the same as 1 minus wn plus 1. So this is the assumption since f is convex. And now inductive hypothesis tells us that this is less than or equal to 1 minus wn plus 1 sum of wj over 1 minus wn plus 1 f of xj, and then plus wn plus 1 f of xn plus 1. Okay, so here I'm using the fact that if you take the sum j equals 1 to n of wj over 1 minus wn plus 1, that gives us sum of wj, j equals 1 to n, divided by 1 minus wn plus 1. And this is 1 by assumption. So because of that, I can use inductive hypothesis, and I would get to that. And then if you cancel these two, you get exactly what you want. Okay, so we proved the Jensen's inequality for convex functions. So now let's look at some of the applications of Jensen's inequality and see how we can use that to prove some of the famous inequalities that you might have heard of. So the first thing is, how do we use that to prove the arithmetic mean, geometric mean inequality? Okay, so arithmetic mean, geometric mean inequality tells us that sum of xj over n is greater than or equal to nth root of product of xj. And this is from 1 to n, j equals 1 to n. Okay, so we're gonna see if we can prove this one. The key here is we need to find a function that is convex and then apply this. If you take natural log of both sides, you will get natural log of sum of xj over n is greater than or equal to 1 over n natural log of product of xj. But natural log of product can be written as sum of natural log of xj, and this over n. Now the weights would be 1 over n. If you look at this function, f of x equals natural log of x. So let's take the derivative of that. derivative of that is 1 over x. Okay, this one is not increasing, so I will have to use something that is increasing. So let me take negative of that. Then what I would get is this is increasing for, of course, x positive. Remember that xj's in AMGM are all positive. So because that's increasing, f of x is convex. And this means if I take minus natural log of sum of xj times some weights, in this case I'm going to choose the weights to be 1 over n, this would be less than or equal to minus 1 over n sum of natural log of xj. And then multiply by a negative sign, flip the direction of inequality, and then raise e to the power of both sides, and then you get the AMGM. So this implies AMGM. Do the same thing with the same function and with some weights, and you will get the weighted AMGM, which is the sum wj xj is greater than or equal to the product xj to the power of wj. If xj is positive, wj is positive, and sum of wj is 1. Okay, so this proves the AMGM and weighted AMGM. Now let's look at some other applications of this. The next application that we're going to look at is the power mean inequality. So first of all, what does the power mean inequality tell us? And then how do we prove that? So the power mean inequality tells us this. Suppose x1 through xn are positive, and we also have some weights w1 through wn are in 0, 1, satisfy sum of wj is equal to 1, j equals 1 to n. Then what we have is this. If you look at this function, sum of wj xj to the power of alpha to the power of 1 over alpha, this is going to be an increasing function. This is going to be greater than or equal to the sum of wj xj to the power of beta raised to the power of 1 over beta if alpha is greater than beta, with, of course, alpha and beta cannot be 0. Furthermore, we can actually find the limit when alpha approaches 0. So here's what it tells us. Furthermore, sum of wj xj to the power of alpha to the power of 1 over alpha is greater than or equal to the product of xj to the power of wj and greater than or equal to the sum of wj xj to the power of beta to the power of 1 over beta if alpha is positive and beta is negative. So in terms of alpha, this is an increasing function, and when alpha approaches 0, it gives us the geometric mean, the weighted geometric mean. Okay, so let's prove this one. So let's assume that alpha is greater than beta, and let's take the case when both of them are positive. Okay, so let me see what I need to prove. We need to prove the sum of wj xj to the power of alpha raised to the power of 1 over alpha is greater than or equal to the sum wj xj to the power of beta raised to the power of 1 over beta, and of course both of these are j equals 1 to n. So here's what we're going to do. I'm going to raise both sides to the power of alpha to get rid of one of the exponents. That gives me wj xj to the power of alpha is greater than or equal to the sum wj xj to the power of beta raised to the power of alpha over beta. Now look at this function. F of x equals x to the power of alpha over beta. Let's take the derivative of that. F prime of x becomes alpha over beta, which is positive, x to the power of alpha over beta minus 1. Since alpha over beta is more than 1, this is in fact increasing. Because this is increasing, that means f is convex. So because f is convex, we can use the Jensen's inequality. So that tells us f of sum of wj xj. I'm going to actually replace xj's by xj to the power of beta. This is going to be less than or equal to the sum of wj f of xj to the power of beta. So let's apply that and see what we get. On the left, what we're going to get is the sum wj xj to the power of beta raised to the power of alpha over beta is less than or equal to the sum wj. If you substitute x by xj to the power of beta, you will get xj to the power of alpha. So this gives us the sum wj xj to the power of beta raised to the power of 1 over beta is less than or equal to the sum wj xj to the power of alpha raised to the power of 1 over alpha. And that's exactly what we wanted. So this is the case when alpha and beta are both positive. Now suppose that alpha and beta are both negative. Suppose beta less than alpha and they're both negative. So what we need to prove is this: the sum wj xj to the power of beta raised to the power of 1 over beta is less than or equal to the sum wj xj to the power of alpha raised to the power of 1 over alpha. What I'm going to do is I'm going to replace alpha and beta by negative alpha and negative beta. So this gives me the sum wj xj to the power of negative 1 raised to the power of negative beta and then raised to the power of negative 1 over beta, that is greater than or equal to sum wj xj to the power of negative 1 raised to the power of negative alpha raised to the power of negative 1 over alpha. So I took the reciprocal of both sides. And of course this is true because negative alpha is less than negative beta and they are both positive. So if you put the negative sign at the bottom, that might be easier to see. The relation between this and what we had might be easier to see. This is the exact same inequality. So this proves the case, this proves the inequality for the case when alpha and beta are both negative. Now what if you approach 0? Let's see what happens. If you take the limit of the sum wj xj to the power of alpha raised to the power of 1 over alpha as alpha approaches 0, we would like to show this is equal to the product of xj to the power of wj, which was the weighted geometric mean. Okay, so how do we prove this one? Now, because when you plug in alpha equals 0, you get an indeterminate form. What you would get is you would get sum of wj's if you substitute alpha equals 0 raised to the power of 1 over 0. Of course, this is 1 raised to the power of infinity. That's an indeterminate form. In order to deal with that, we will have to take natural log and then use L'Hopital's rule. So we'll do that. So we'll take limit as alpha approaches 0 of natural log of sum of wj xj to the power of alpha and then divided by alpha. Now this is natural log of 1 divided by 0 when you plug in alpha equals 0. This is now indeterminate form of 0 over 0, so we can use L'Hopital's rule. The denominator becomes 1, numerator becomes derivative of this, which is sum of wj xj to the power of alpha natural log of xj divided by sum of wj xj to the power of alpha. As alpha approaches 0, the bottom becomes sum of wj and the top becomes sum of wj natural log of xj. Bottom is 1, the top is the natural log of product of xj to the power of wj. And of course, when you want to take the limit of what we started with, we have to raise e to this power. So the limit as alpha approaches 0 of sum of wj xj to the power of alpha to the power of 1 over alpha is going to be product of xj to the power of wj, j equals 1 to n. Now we know that when alpha approaches 0, we get that quantity. So we know that the power mean is increasing, and at 0, we get this quantity. So it would be increasing everywhere, and at 0, you can define it this way. And that gives me the power mean inequality, which in turns, you can get all of those other inequalities. So if we go back and look at what we had at the beginning, you can get the harmonic mean by substituting alpha equals -1. So if you substitute alpha equals -1, you get the harmonic here. Substitute alpha equals -1 and wj is equal to 1 over n, you get to that. So this is alpha equals -1, wj equals 1 over n. This one is alpha equals 0 basically. This one is alpha equals 1 and same wj's, and this one is alpha equals 2. And that brings me to the end of this video. If you like this video, feel free to check out the rest of the videos on my channel, and I will see you in the next video.